Let's look at some of the things related to the stereochemistry of an SN1 reaction. And the SN1 reaction that we're going to look at today starts with T-butyl chloride. I've colored my different methyl groups different colors so we can keep track of them. And as you've talked about before, when you do an SN1 reaction, the first step is for the leaving group, which in this case is a chloride atom, or a chloride ion, leaves. That's the first step. And I've shown that here with this arrow, generating this planar carbocation. And what I want to do is I want to look at the three-dimensional structure of the process that's going on here. So I want to look at a three-dimensional model of it. And here's our three-dimensional model. This is my chlorine that's going to turn into the chloride ion when it leaves. And again, as in this model, I've colored my methyl groups different colors so I can keep track of them. So if we look at what happens over here, the chloride ion starts to leave. So we can show that bond getting longer as the chloride ion pulls away. And finally that bond breaks. Now that's not the only change that happens in this process. You'll notice I've drawn this structure a little differently because this, which is now a carbocation and is sp2 hybridized, becomes trigonal planar. So what happens is, and I'll try to drag the methyl groups all into the same plane, as that chlorine is leaving to form a chloride ion, the carbon that is now sp2 hybridized becomes trigonal planar, like that. Now that we have our planar carbocation, the next thing that happens is that a nucleophile comes in and reacts with the carbocation. Now, since this carbocation is planar, and since it looks basically the same from either side, and if I look at my model, whether the nucleophile sees this side of the molecule or this side of the molecule, it's seeing essentially the same sp2 hybridized carbocation. So it can attack from one side, it can attack from the other side. If it proceeds as shown in this instance, attacking from the way I've drawn it, the left face, what we end up getting is this product where my nucleophile is coming out from the left side of the molecule the way I have it drawn, and my three groups have been pushed back to the other side, and I now have my sp3 tetrahedral shape returned. Now on the other hand, if the nucleophile attacks from the other side, my product has the nucleophile projected to the other side as shown here when my sp3 tetrahedral shape returns. Now we could do the same thing with our three-dimensional model over here. So if we look at this product first and we show our nucleophile coming in from this side as it approaches this carbon, these groups start to move back and like this. This hydrogen probably is not like that. And it comes and eventually makes the bond there to give us a product that looks like this one over here. And I can spin it and look and see that it's tetrahedral again. And again, oops. And again resembles this here. Now, on the other hand, I could draw my nucleophile attacking from the other side. In this case, the nucleophile comes in from the other face of the molecule, and as it comes in and starts to form a bond with the carbon, the methyl groups start moving away. And finally, a new bond forms between these two atoms, giving us a product that resembles this one drawn here, where the nucleophile is on the opposite face. If we compare this model to the original one the way we did over here, we see that the two are mirror images of one another. Now, in this particular case, that doesn't matter because even though I've colored them differently, all three of these are methyl groups. So this is actually the same product as this because there's no stereocenter in this molecule. But you can easily see that if these had been three different groups, that I would have ended up with two different products over here that were non-superimposable mirror images of one another or enantiomers.